Hi students, in the second video of online lecture 11, we're now going to talk about the formal charge rules. So what is formal charge? Well, for a neutral molecule, a Lewis structure in which there is no formal charge is preferable to one in which formal charges are present. The formal charge is talking about the number of electrons signified on your Lewis structure. As you're bringing the electrons in, they are going to distribute to all of the various atoms, but they may not distribute equally. So now the molecule may have little itty bitty charges in locations that it didn't originally have. So then for 2, it is saying that the Lewis structure with large formal charges are less plausible than those with small formal charges. The small formal charges that we want are going to be -1, 0, which is neutral, which goes back to rule 1, and r plus 1. We want to stay away from anything that is typically +2, -2, or higher. So then 3, among Lewis structures having similar distributions of formal charges, the most plausible structure is the one in which negative formal charges are placed on the more electronegative atom. We typically call this the more electronegative rule. Be very careful with that as you are starting to go along. So let us look at 2 possible skeletal structures for the molecule formaldehyde. This is going to show you the importance of our structures. So now what can we do? Well, let us go ahead and look at this as our first possible skeletal structure, and here is our second. So let us go and look at what formal charge means. This is the difference between the number of valence electrons in an isolated atom, that means coming from the periodic table, and the number of electrons assigned to that atom in its current Lewis structure. So now, one way of calculating formal charge is by using the formula that you'll see below. That is the total number of valence electrons in the free atom. This is coming from our periodic table. This is where you need to know the column that it is in and how many valence electrons you are going to get. Then what you're going to have is you're going to subtract the total number of non-bonding electrons. These are your lone pairs. These are electrons assigned specifically to that atom that are not being shared with any other bonding atom. And then finally, 1/2 the total number of bonding electrons. So this is 1/2 of our bonding pairs. Now, this is not how I originally learned how to do this. So when we are working on this, the best way of looking at it would be what electrons were brought in and how many does it currently have. So the sum of the formal charges of the atoms in a molecule or ion must equal the charge of the molecule or ion. So if we are working with something, let's say that we have CO3 2-, our overall molecule at the end must have a -2 charge, and that must be distributed over the molecule in some way. That can also be true if we look at a molecule such as NO3 1-, our nitrate anion. We would have one atom holding on to that -1 charge. So let us go and see what is right and wrong for formaldehyde. So here is our first structure. Notice that my carbon brings 4, my oxygen brought 6, and each one of my hydrogens brought 1 electron for a total of 12 electrons. Those 12 electrons are now put on this molecule. You can see here that I have 2 single bonds, I have 1 double bond, and I have the 2 lone pairs, 1 lone pair on the carbon and 1 on the oxygen. So now let us go and do our formal charge calculator. So as we can see here for the carbon, it brought 4 electrons. That can be seen right here. That is always going to be the case for carbon. Then what we are going to do is have -2. Well, where did that 2 come from? That is the total number of non-bonding electrons. Those 2 are our lone pair right here. And then finally, we are going to have minus 1/2 times 6. The 6 electrons that we are going to look at are the 4 here in this double bond and 2 electrons that we have in the single bond. That is 6 total electrons, but we get 1/2 of them. So if we take 4 minus 2 minus 1/2 times 6, we are going to get a formal charge on carbon of -1. This has a negative charge. The way I calculate it is a little bit more straightforward and does not use the formula. Typically, what I will say is electrons coming in So in this case, that is going to be the 4 that we have here minus the electrons it has now. For our lone pair, we are going to count those just specifically for our atom. For bonding pairs, we are going to only count 1 electron per bond. So in the case of our carbon, I would have counted 2 for our lone pair, and then I would count 1, 2, and 3 for my bonding pair. So that makes a total of 5 electrons that it has currently. So if you do that, I would end up doing 4 electrons in minus the 5 electrons that it has, and you will see that I end up in the exact same spot as -1. Either way of doing this is acceptable. So now let us go ahead and notice the formal charge on the oxygen. How many electrons did the oxygen bring in? Well, it brought in 6. So we have 6 electrons. Does it have a lone pair? Yes, it does. So that is where we are going to subtract 2. And then how many bonds does it have currently to our species? Well, you will notice that it has 3 bonds. So we would end up having 6 bonding electrons times 1/2. And you will ultimately notice that we end up getting a charge of +1 on our oxygen. Had I done my math, I would have taken the 6 electrons it brings in. We have 2 lone pairs, or we have 2 electrons with the lone pairs, and then 3 electrons from the bond. So I would have done 6 minus 5. That comes out to a +1. And so now we end up getting our oxygen with a formally +1 charge. Now let us go and look at our next example. Here is the other structure of formaldehyde. You will actually notice that the atoms are connected differently. In the last example, we had a hydrogen connected to the oxygen, where now both hydrogens are connected to the carbon. This is what we call a constitutional isomer, or just an isomer. This means that the atoms are connected differently. For resonance structures, we just showed electron movement. If in the case of atoms actually moving and the connectivity is different, that is what we are going to call an isomer. So now you can see that we have the same number of electrons coming in because we have the same atoms that we are connecting. We have 2 single bonds. The carbon-hydrogen bonds are those single bonds. We have 1 double bond from our carbon to oxygen. And finally, we have 2 lone pairs on the oxygen. So here is our formula once again. So let us go and calculate the formal charge on my carbon. It brought 4 in. It currently has no lone pairs. So we have 0 for our second number. But how many total bonding pairs did it have? Well, it has 4 bonding pairs at 8 electrons. So we would take -1/2 times 8. That gives us 4. So we end up getting 4 minus 4 is 0. Using my math, we would have brought in 4 electrons, and then notice that we have 4 bonds, all split equally. So that means that I would get 1 electron from each one of those bonds, and I would end up with a neutral formal charge on my carbon. So now let us go and look at our oxygen. Our oxygen brought in 6, which is the same from the last example. Now, notice that we are going to have 4 valence electrons that are our lone pairs. 2 pairs with 2 electrons means 4 free electrons. But then also notice that we are going to have 2 bonds. So in this case, that is going to be 4 electrons times 1/2, and we are going to end up getting 0 as well. Had we done my math, I would have gone and had 6 electrons in. I would have then had the 4 electrons from the lone pairs, and then 2 electrons from the double bond. So 6 minus 6 is equal to 0. Now I have a molecule in which I have no formal charge. So this is going to be the best structure when we talk about the ideas of formal charge, because Rule 1 said we want to have the least number of formal charges possible. On the last example, we had a +1 and a -1, which was good because they were small formal charges, but this molecule is better because there are no formal charges. We prefer to have neutral species in our molecules. So this is the structure we end up with. We are going to talk about molecular geometries when we get to the next chapter. So let's look at these examples here. Considering the following resonance structures of methylamide, which of the following structures is most stable? Most stable, meaning it has the lowest energy, which means it has the best formal charges. So what we want to do here is go and look for, first off, our octet rule to see if it's satisfied, and then we want to look at our formal charges. So let us look at A. The biggest concern I want you to see for A is this carbon right here. Notice that it currently has only 3 bonds. It is missing 2 electrons to its octet. So naturally, this is not going to be a very stable molecule. So for our species A, this is not going to be a correct answer. That is going to get rid of answer A and answer E. So let us go ahead and look at B. Notice that all of my atoms do have an octet. So let us go and try and determine which species has formal charges. So if I look at my oxygen here, it originally brought 6 electrons in. Currently, it has 7, because right now what we have is 3 lone pairs, 6 electrons, and 1 electron from the bond between carbon and oxygen. This is going to give us a formally negative oxygen. Our carbon is neutral, but let us go ahead and now look at this nitrogen. Nitrogen brought in 5 electrons, but currently it only has 4 electrons, 2 from the double bond that we see here, and 1 each from the bond going to this hydrogen. This is going to make this nitrogen formally positive. So right now, we have for species B, a formally negative oxygen, which is good because of the fact that we have our most electronegative atom having the negative charge, and our nitrogen being formally positive. Let us go and look at example C. Notice that my oxygen now has a different look to it comparative to B, and if it brought in 6 electrons, you will notice that it currently has 6 electrons, that being 2 from our lone pair here, 2 more, that gives us 4 from the lone pair, and we're only going to count 2 electrons from our double bond. This is going to make that oxygen formally neutral. In the case of our nitrogen down here, notice that I have brought 5 in. It currently has a lone pair, so there is 2 electrons, and it has 3 bonds. So we are going to count 1 electron from each of those 3 bonds. It brought 5, it has 5, and it's formally neutral. So for answer C is better than answer B because we have no formal charges. So answer B cannot be the correct answer. Let us go ahead and look at example D. Can anybody see the biggest mistake in here? And even though it looks very similar to that of our answer B, we have a huge problem, and that problem is right here. Notice that my carbon right here has 5 bonds. This is violating the octet rule. So this cannot be a valid answer. Our carbon has a double bond to the other carbon and 3 hydrogens attached to it. Therefore, D is not allowed. This violates the octet rule. So our correct answer for this example problem is going to be answer C. Make sure that you are working on calculating the formal charges of all of your species. So now let's try this example. Considering the following resonance structures for the arsenate ion, which of the following structures is the most stable? So one of the things that's going to happen is that you are going to see that certain molecules, when they break the octet rule because they are row 3 and below, are going to adopt the formal charge rules for stability over the octet rule. So let us look at answer A. Notice that this species has a really good octet for all of the atoms. But let's look at our middle arsenic right now. Notice that it brought 5 electrons. It currently only has 4, so now we get a formally positive located on our central atom. For each one of our oxygens, notice that there are 7 electrons around them, 6 from the lone pairs and 1 from the bond to the arsenic. So each one of these oxygens is going to be considered formally negative. This has a lot of small, good formal charges. But let's go and look at answer B. What have I done by going and violating the octet rule and going to the expanded valence? Notice that I have brought a double bond in, and this oxygen is now currently different than all of the others. This is formally neutral. What about my arsenic? Well, it brought 5 electrons, and now it has 5 bonds. This means that my arsenic is also formally neutral. The remaining ones of my oxygens are negative, and you will now notice that this has reduced some of the number of formal charges in our molecule. Currently, B is going to be more stable than A. So A can no longer be a possibility. We will also get rid of answer E. Let's go ahead and look at answer C and notice that I have doubly bound all of my oxygens. Well, now let us focus in on our arsenic. It brought 5 electrons in. Now it has 8 total bonds, so 5 minus 8 is going to be minus 3. All of our negative charge is located in on our central atom. This is a large formal charge. This is going to disqualify answer C. Let us go and look at answer D. Notice that I have 2 double bonds, so now we are going to have a negative on one oxygen, negative on this oxygen. The top and bottom oxygens are going to be formally neutral, like the top oxygen in B. But now let's look at our arsenic. It brought 5, but now it currently has 6 bonds. So 5 minus 6 is minus 1. And now notice that I have a negative on that arsenic. So what does that mean for us? Well, that means that we are going to have 3 negative charges all in a row. One rule that was not listed originally is what we typically call the same charge rule. We do not want to have the same formal charges near each other because they are going to repel just like most electronic properties. So by having all of this negative electron density is actually going to destabilize our molecule. The other thing is we are going to have a negative formal charge on an atom that is less electronegative than either one of these oxygens. That is violating our formal charge rules. So answer D is not correct as well. This means that our best structure is going to be answer B. So when dealing with our resonance structures and determining formal charges, you want to always think about the octet rule, especially those for our second row species, carbon, nitrogen, oxygen, and fluorine. As you get to row 3, and as you're going to see in the next chapter, once we get to some of our molecular geometries of our expanded valence molecules, the formal charge rules are actually going to take over and help signify the stability of many of our molecules. In this video, you saw the importance of the formal charge and how to calculate the formal charge for any of our molecules that we are going to have from here on out. Have a great day.